Yes, Sahil, still you are not able to share now.
I am not the co-host, sir.
Hmm. Yeah, can you try? Yes, Satvik, okay. Sahil, iPad na?
Yes, yes.
Yeah, done.
Should I start?
Yeah, yes, Sahil, you can start. Sahil, you are not audible.
Yeah, am I audible now?
Yes, you are now audible.
Yeah. So, welcome to this live session for week 10. And I was saying that we have two questions for this particular week. Both of them are based on DP, which is considered to be the one of the difficult topics in CP. And it is also, if we consider from interview perspectives, it is one of the most important topic because many companies ask questions based on DP. So yeah, let's dive into the first question and see what it asks for. So yeah, I hope the question is visible. So let's read the question properly. As a professional robber, you want to rob houses on a street. However, there is a security system that will trigger a police response if you try to rob two adjacent houses, right? And each house has a certain amount of money stored, and you want to maximize your profits without alerting the police. Okay, so basically, you are given an integer array nums that represents the amount of money in each house, and your task is to determine the maximum amount of money you can steal tonight without triggering the security system. Okay, so the question is very simple. You are a robber, and let's say there is a array of integers. So every integer represents the money stored in the ith house. The ith entry will represent this, and you just as a robber, your goal is to rob the amount of money maximum amount of money without alerting the police. Okay, so you cannot rob from two adjacent houses. If you try to rob this house, you can't rob this house. So if you try to rob this house, you can't rob this house. So this needs to be kept in mind. This is the condition to solve this question. Now if we consider the input, the first line of the input contains t, the number of test cases. The first line of each test case contains an integer n representing the number of houses on the street. So this is basically the size of the array, okay, which is n. And the second line of each test case contains an array nums of size n representing the amount of money stashed in each house. Okay, so the input is quite simple. You have t number of test cases. For each test case, you will have an integer n, which is represents the size of the array. And the next line will have the entries of the array. Okay, so the input is quite simple. Now talking about the constraints, which I've always told becomes a very important factor when you are trying to solve a competitive programming question, because you always want to design your algorithm in such a way that it does not exceed the time limit. So let us assume that here the time limit is 1 second. That means we can do 10 power 8 operations. So that certainly means that our algorithm, the time complexity of our algorithm should be less than equal to 10 power 8. Okay. So let's consider the constraints here. We have t, we have n, and we have nums of I. So t is from 1 to 100, n is from 1 to 500, and nums of I. Okay, so n is from to 10 power 5. Sorry, n is still 10 power 5, and nums of I is still 500. Okay. So now, our algorithm will definitely not consider this one because these are the array entries. So we need not take care of this. It's just a constant. So now talking about this, let's say we have t test cases and n is the size of the array. So let's say for each test case, if we traverse the array linearly, then the time complexity will be order of t into n, because for each test case we are taking order n time. This will be order of 100 into 10 power 5. Why 100? Because the maximum limit of t is 100. Why 10 power 5? Because the maximum limit of n is 10 power 5. So this becomes order of 10 power 7, which is definitely less than equal to 10 power 8. So I am sure that a linear algorithm would work. Perfectly fine. Okay. Instead, if I consider order of t n square, that is for each test case, if I try to do a quadratic solution, then the time complexity will be order of 100 into 10 power 10, which is nothing of order of 10 power 12. That is greater than 10 power 8. Okay. So obviously we cannot propose an algorithm which takes order of t n square solution, a quadratic solution. We cannot do that. So we just have only one option, which is we have to solve this question in linear time. How will we do it? Let's see. Okay. Now, understanding the output, we just have to print a single integer which indicates the maximum amount of money that can be robbed without alerting the police. Okay, it is simple. You pick up the integers from the array in such a way that you do not pick up integers in adjacent manner, and in this way you need to maximize the sum of the integers you picked from the array. Okay, so we have boiled down the question. We have forgotten all this robbery in all those houses. We just have framed the question in simple algorithmic way. There is arrays and integers. Okay. Now let's say understanding the input. These are some sample test cases. Let's try to come up with a solution. Okay. So the sample is, we have two test cases. The first test case has an integer array size of 3 and the values are 1, 2, 4. This is the array. And the next test case has the value of n, which is the size of the integer array, as 4, and the array is 2, 1, 4, 9. I hope I have written it correctly. Let's see. Yes. Okay, so this is the thing. Consider this array 1, 2, 4. 1, 2, 4. If I pick one, I cannot pick 2. Let's say if I pick 1, I cannot pick 2. I can pick 4. So the answer will be 5. 1 plus 4. If I pick 1, I cannot pick 2. If I choose to not pick 4, the answer is 1. Let's say if I don't pick 1, I can pick 2. And because I have picked 2, I cannot pick 4 because it is adjacent to 2. So the answer will be 2. If I don't pick 1, if I choose not to pick 2, and if I choose to pick 4, the answer is 4. And as you can see, The maximum of all these numbers is 5. Okay, so for this array 1 to 4, the maximum you can pick such that the sum of the picked elements, non-adjacent obviously, sum of the picked elements is maximum is equal to 5. Okay, it is equal to 5 here. Let's see our answer. What is the output? Yes, it is 5. Okay, now the next test case, which is the array 2 1 4 9. Okay, let's try to explore all possibilities of picking and not picking, and then we will derive the answer. Let's see. If I pick 2, then I cannot pick 1, and if I choose to pick 4, I cannot pick 9. So the answer is 6 here. Okay, if I pick 2, and if I choose obviously, like if I have picked 2, I cannot pick 1, and if I choose not to pick 4 and I choose to pick 9, then the answer is 11. Okay, let's say I don't pick 2, I pick 4, I pick 1. Now I cannot pick 4 because I've already picked 1, which is adjacent to 4. So I don't pick this. I pick this. Answer is 10. Okay. Let's say I don't pick this. I don't pick this. I pick 4. I cannot pick 9. So the answer is 4. I don't pick this. I don't pick this. I don't pick this. I pick 9. Answer is 9. Okay. Some other possibilities could be. I think these are the possibilities. So, oh, sorry. Yeah. So out of these numbers, the maximum which we are getting is 11. So 11 should be the answer. Let's see what is the answer. Yes, it is 11. Okay. So we are getting closer to our algorithm, or let's say we are getting closer to the idea of what we are doing. So we have an array from A1, A2 up to AN. What we are doing, we are exploring all possibilities. This is a very important word, exploring all possibilities. We are trying all possibilities, and out of all these possibilities, we generate the maximum answer, right? Because maximum is asked in the question, right? So one naive solution could be to use recursion, right? We can always use recursion, right? Because let's say I have 2 1 4 9. What recursion can do? It can pick 2 and find the answer of this one. Like what recursion can do? Let's if we try to apply recursion, what will recursion do? We have 2 1 4 9. Recursion says that output the maximum of the following. Let's say this is 0 index, 1, 2, and third index. What do? We pick A of 0. This is array A, let's say. We pick A of 0 plus recursion calls from 2, 3. So what we have done, we have picked A of 0. That is, we have picked 2. And we have called the recursion on this array. Why haven't we called the recursion on this array? Because we have picked 2. We cannot pick the first element, right? That is why we call the recursion on 2, 3. The second option could be to not pick 2 and call the recursion on 1, 2, 3. Call the recursion on 1, 3. Okay, so 1, 3 is the array 1, 2, 3. Okay. So output the maximum of this. This will be the maximum, right? Yes. Why? Because let's say we have 2, 1, 4, 9. And the first case was to pick 2 plus the maximum of this. The maximum of this array could be 9, right? Because the possibilities are you either pick 4 or you pick 9. So obviously maximum will be to pick 9. So 2 plus 9 will give us 11. The second possibility was to not pick 2 and find the maximum answer in this one. Maximum answer will be 1 plus 9, which is equal to 10. So the maximum of these two is 11. So recursion is giving us a very good answer. So just to formalize what recursion does. So recursion, let's say if we have an array A, and let's say if we consider one based indexing 1 to n sized array 1, 2, 3, 4, 5 up to n are the indices. What will recursion do? Let's make a tree. Let's make a tree. F of 1, n. So this is the final answer which we want to output. Okay. F1, n. What will it will do? It will break the array into two parts and will call recursion. What it will do? It will pick the first element and will call the recursion from the third element. Right? This is pick and this is not pick. So it will not pick the first element and it will call the recursion on 2, n. Right? Okay, now this is done. On this f of 3, n will again have a recursive solution. So what it will do? It will pick or it will not pick. So f of 3, n can do pick a of 3 and call f of 5, n. What will not pick do? It will not pick a of 3 and will call the recursion directly from f of 4, n. So like why is this happening? Because we are picking the third element, so we cannot pick the fourth element. That is why the recursion calls from the fifth element. Okay, so this is the basic funda. Now this one also, it will pick or it will not pick. If it picks the second element, then a of 2 plus f of 4, n, because the third element cannot be picked. And if it is not picked in the second element, then the recursion will be called from the third element. Okay. So in this manner, the tree goes on. Okay. In this manner, the tree will go on, Okay. So now let's see. In this path, you calculate f of 3, n. And in this path, you are again calculating f of 3, n. So why to do computations multiple times for the same thing, right? It is just waste of, like it is not efficient, right? Let's see, let's see one more example. We are calculating f of 4, n here. We are again calculating f of 4, n. Why are we doing this computation multiple times? This is just inefficient, right? So this condition is called overlapping subproblems, right? This is a very important term when you are trying to come up with a dynamic programming solution. And dynamic programming is understood in this manner only, that we have a question, we try to think about all the possible cases. And whenever we hear the word all the possible cases, we directly go to our beloved recursion. But actually it is not beloved, because the time complexity of recursion is exponential. So we don't like recursion, and that is why some geniuses, some experts have found out an alternative of recursion, which is BP. Okay, so I've explained how to break down the problem into these sub problems, and if you find overlapping sub problems, then you should quickly decide that okay, this is a dynamic programming question, right? So because we are computing the same value again and again, why to do that? Why to become so inefficient? We are programmers, right? We want to do something good. We want to make algorithms efficient, right? So this is overlapping subproblems. So we will not use recursion because this will give us a complexity of 2 power n, which is exponential complexity, right? Because for each thing we are taking two choices, right? So it is like a binary tree, right? It is like a binary tree. We're going here, going here, going here, going here, right? And to traverse the whole binary tree, how long it takes? The height, let's say, if there are n nodes, then the height will be log of n, right? Log of n. So you go here, you go here, you go here, and then you go here. This takes exponential time, right? Exponential time to traverse a tree takes exponential time. Okay, so obviously we just calculated that order of t into n, which is linear, takes 10 power 7 operations. 10 power 7 operations. Obviously, if we'll do exponential with this 2 power n, this will be huge, right? 2 power 10 power 5. This is close to infinite value, obviously. So we cannot obviously cannot do this. So we'll discard this one. So we now know that the concept is about overlapping subproblems, right? And the main problem which we are encountering is that we are again and again computing the same value, computing for the same subproblem, which we want to avoid, right? So for our rescue, dp comes. Okay, so we'll try to apply dp. Okay, so yeah, let's say we have our array. Let's consider one based indexing from 1 to n. Okay, so what we were doing, our final answer, which was f of 1 comma n, was dependent on two factors, f of 3 comma n and f of 2 comma n, right? F of 2 comma n was dependent on two factors, f of 3 comma n and f of 4 comma n, and so on, right? So try to think if we have this array, if we say, let's say, how we apply dp. Okay, so for a dp we will make an array. Okay, we will make a dp array from 1 to n, again one based indexing. What can we say? And if dp of i represents f of I comma n, okay, so what will dp of 1 tell us? Dp of 1 will represent f of 1 comma n, which was the final answer, right? Just a minute. Yeah, okay, so yeah, let's forget these things. Yeah, so I'm considering f of 1 comma n, which gives the answer for the whole array, right? For the whole array. Okay, for the whole array. So let's say if dp of I represents f of I comma n, then what will dp of n tell us about? Dp of n will represent f of n comma n, which is only the last element. Okay, which is only the last element, right? So what will be f of n comma n? F of n comma n will be the value of the last element itself, right? Because if the size of the array is only 1, then what is the maximum amount that we can get by picking or not picking? Obviously we'll pick the element x, right? So the answer will be x, right? Okay, so this is the case of the array where the size is 1. Okay, the size is 1. Okay, let's say if we consider dp of n minus 1, which will represent f of n minus 1 comma n. So this will depend upon, let's say this one picks the n minus 1th element, and now it cannot pick the nth element. So we don't have anything here, we have 0. And if it chooses to not pick, then there will be 0 plus f of n comma n, right? Right, this is one thing. Now let's say consider dp of I. dp of I will represent f of I comma n, which will again depend upon two factors, pick and not pick. If picks, then a of I plus f of I plus 2 comma n, which is nothing but a of I plus dp of I plus 2, because dp of I is representing f of I comma n, right? And if you're not picking, then 0 plus f of I plus 1 comma n, which is nothing but 0 plus dp of I plus 1, right? Right. So what we are doing is we are considering this array. We are considering this array, and we are assuming that till here we know the answer. Till here we know the maximum answer. And now for the ith element in this array, we want to so like what we are doing is we want to find the answer for the array for the array 1 to I. Okay, and this is represented by dp of I. So, and ultimately our final answer will be dp of n, because that will be the answer for the whole array. Okay, 1 to n. So let's say this is 1, this is n, and let's say till here this is the ith index. So dp of I will be nothing but maximum of pick comma not pick. Okay, so what does this pick comma not pick mean? So dp of I will be nothing but maximum of picking the ith element comma not picking the ith element. So maximum of picking the ith element, that means I picked the ith element. Now can I do dp of I minus 1? No, I cannot do dp of I minus 1 because I've picked the ith element. So I cannot pick, because dp of I minus 1 will also comprise of picking the I minus 1th element, right? So we cannot do that. So what we will do, instead of dp of I minus 1, we will do dp of I minus 2. Okay, and comma not pick case. We don't pick a of I. So 0 plus dp of I minus 1. Here we can do I minus 1 because I minus 1 considers all the cases. So it will include the cases where we have picked the I minus 1 element also. And if we are not picking the ith element, we are allowed to pick the I minus 1th element, right? But in this case, when we have picked the ith element, we are not allowed to pick the I minus 1th element. That is why we are taking dp of I minus 2, which counts for all the cases where I minus 1 is not considered. Okay, so this is the thing, and we have solved this question. We have literally solved this question. So just need to think like what will dp of I? dp of I will be maximum of, if you have picked the ith element, then this, and you have not picked the element in this one, and you do this for all i's from 1 to n, and the final answer will be, the final answer we want is for the whole array 1 to n. So the final answer will be dp of n. Okay, considering one based indexing. Okay, and in my code, in my solution, which I will show in just a few minutes, I've considered 0 based indexing. So there the final answer is dp of n minus 1. Okay, because I've considered the array from 0 to n minus 1. So but the logic remains the same. Okay, logic remains the same. So yeah, like we have come so far that we thought about all possible cases. Then we thought about recursion. Then we found out a major problem in recursion, which is of overlapping subcases, overlapping subproblems, right? Overlapping subproblems. And then DP came to a rescue, and we solved the question in linear time. Okay, linear time. Okay, so let's diagram the dry running our algorithm on one of our test cases, Let's say the test case is 2149. Okay. The main equation which we want to remember is dp of I is maximum of a of I plus dp of I minus 2 comma dp of I minus 1. Right. This is the equation we want to remember. So let's start from this position. Okay. We have a new dp array which is everything is initialized to 0. Okay. So dp of 0, if we consider the 0 based index in 0, 1, 2, 3, dp of 0 will be max of, if I pick the 0th element which is 2 plus dp of minus 2. dp of minus 2 is not defined. Okay, so we'll not take that into account, comma, if we not pick this element, so this will be dp of minus 1. Again, this is will not be taken into account, so the answer is maximum 2 comma 0, which is equal to 2. So what does dp of 0 represent? dp of 0 represents the maximum answer which we can get by considering the array 0 comma 0. That is, only one element is there. So obviously the answer will be, the maximum answer we can get is by picking the elements. That is why it is 2. Okay. So now let's say dp of 1. dp of 1 is maximum of, if I pick the first element which is 1 plus dp of 1 minus 2, which is dp of minus 1, which is nothing. Okay. If I choose not to pick the element, then this will be dp of 0. Okay. If I choose not to pick the first element, then this will be dp of 0, which is maximum of 1 comma 2, which is again 2. Okay. So what does dp of 1 represent? dp of 1 represents the maximum answer which we can get by considering the array 0 comma 1. And what is this array? This is 2 1. This is the array. And see, just by observing, what is the maximum answer which we can get? Either we pick this. If we pick 2, we cannot pick 1. If we do not pick 2, we can pick 1. So in this case, answer is 2. In this case, answer is 1. So what is maximum answer is 2. And that is what dp of 1 is giving us 2, right? So moving forward, dp of 2 is maximum of a of 2, which is, I pick the second element, which is 4 plus dp of 0. And if I don't pick, then this will be dp of 1. So this is maximum of 4 plus 2 is 6, and dp of 1 is 2, which is equal to 6. So dp of 2. And similarly, if you have dp of 3, which is maximum of 9 plus dp of 1 comma dp of 2 is nothing but maximum of 9 plus 2 comma 6, which is nothing but maximum of 11 comma 6, which is 11. So dp of 3 is 11, which is nothing but a final answer. dp of 3 represents the answer which we can get by considering the array 0, 1, 2, 3, right? Which is the whole array. So we have got the answer. So see how the algorithm works here. Okay. Yeah, I think that the algorithm should be clear. It is quite simple. Whenever, like I'm telling you guys a trick, that whenever you encounter such a situation in which you need to explore all the possible cases, which was in this question, always think about dp. All the, like, you could find a question where it asks for minimum or maximum or count, but if you need to consider all the possible cases, then think about dp. Okay, so this is one observation which you guys need to keep in mind, that whenever you detect a pattern which requires considering all possible cases, all subsequences, all substrings, right, all subarrays, think about dp. 90% cases you will be able to solve that particular question by using dp. Okay. So yeah, this was all about the algorithm. We have understood the algorithm. We have understood the core of dp, how to approach a dp problem. This is the manner in which you guys should do it, and with practice you will be able to sense a dp problem very, very, very fast, and you will be able to come up with solutions more rapidly, more quickly. Okay, so let's now jump onto the code. The code is very, very simple, as you guys would have guessed. This is a very simple code. And the problem is based on the pick not pick technique. Pick not pick technique, which is a quite famous technique in DP questions. You get questions uh, like try all possible subsequences, try all possible sub-arrays. Right? In those questions, you try to like always try to think about pick not pick technique. Either you're picking the ith element, or if you don't pick the ith element, no, then take the minimum of these two, or take the count of these two, or take the maximum of these two. These type of problems come up very frequently in competitive coding. Okay, so yeah, let's now jump on the solution. Solution is quite simple. We input the number of test cases, then we take the integer n, which is size of the array, then we input the array itself, elements of the array. Now we make a DP array. DP array, every element is initialized to 0. Okay. Now what do we do for I equal to 0? Is the first element, what will be the DP of I? DP of I will nums of I. That is obvious, right? So for an array which contains only one element, what is the maximum answer which I can get? The maximum answer is that element itself. So that is why we have done DP of 0 equal to nums of 0. And if I is equal to 1, we take two cases where we pick or we don't pick, and we consider the maximum. And else, if I is not equal to 0 or 1, then again we take two cases, either we pick or we don't pick, and we take the maximum of these. And finally we print the answer DP of n minus 1. And here DP of n minus 1 is the final answer because we have considered zero based indexing. Okay. So you guys must be confused about why I equal to 1 and the rest I cases have been treated separately. This is because for I equal to 1, DP of 1 will be maximum of A of 1 plus DP of minus 1 comma DP of 0. Okay. So minus 1 is obviously not valid. Minus 1 index is not valid. That is why we are discarding this. We are treating this as 0. And that is why we have considered I equal to 1 and all other i's separately. Because for all other i's, I greater than equal to 2, maximum of A of I plus DP of I minus 2, comma DP of I minus 1. This DP of I minus 2 will be greater than equal to 0. This is a valid index. But for I equal to 1, I minus 2 is equal to minus 1 is not a valid index. That is why we are treating it separately. Okay. So I think the algorithm should be clear. And I must say that thinking about a DP approach is difficult, but the moment you are clear that you know that you have to apply DP problem and you know how to do it, the equation, you find some 2 or 3 equations. Like in this case, the equation was DP of I equal to maximum of A of I plus DP of I minus 2 comma DP of I minus 1. But this is a very simple equation, and just you have to run a simple for loop and you're done with the question, right? So this is the beauty of DP. And but like to think about DP needs practice, and that is where people mostly get stuck into. But I'm sure that if you try and practice more about DP problems, you will sense patterns in DP problems, and eventually I think you'll become good at solving questions related to dynamic programming. So yeah, that's all for week 10 programming question 1. Now I will hand it over to Satvik for explaining the question and solution of the second question. Yeah, thank you.
Thank you, Sahil. Okay, so week 10 programming assignment question number 2. So what we are given is that the definition of a beautiful sequence. It is a sequence containing only zeros and ones, and such that no adjacent values in the sequence are the same. So 0 and 1 occur as in there are only 2 possible digits in the sequence. They occur in alternate because no adjacent values can be same. And we have been given example that 010 is a beautiful sequence, but 011 is not because 11 occur in adjacent positions. Now you have been given an input integer n which denotes the size of a beautiful sequence starting with 0. Now, this is another constraint on the input that we are given, is that the sequence or the beautiful sequence, it starts with 0. So input is in form of something like 0, 1, 0, 1. Okay. And it just goes on. So if for n equals to 1, it's 0. For n equals to 2, it's 0, 1. N equals to 3, 0, 1, 0. N equals to 4, 0, 1, 0, 1. 0, 1, 0, 1, 0, and such that. Okay. And now determine the number of beautiful subsequences of the given sequence. Now, what you have to do is determine the number of beautiful subsequences. So you don't have to just determine the subsequences, but there's a constraint that the subsequence should also be beautiful. That is, the adjacent values should be different in the sequence. A subsequence is a sequence that can be derived from the given sequence by deleting 0 or more elements without changing the order of the remaining elements. Right? So if this, okay. Yeah, let's take an input example only. What we are given. Okay, let's look at the constraints. And ranges from 1 to 10 power 6. And we haven't given the value of the mode also. Now, if you are given input as n equals to 3, this means you have been given input as 0, 1, 0, right? You have to interpret it like that. And now what would be the number of possible subsequences of this? Well, subsequences could be, okay, let's denote it index-wise, 1, 2, 3, right? Because the 0 at index 1 and the 0 at index 3 are different, okay? So that is why number of subsequences would be 0. If you take it 1 and 1 at the position 2, 0, 1, that is 1, 2. 1, 2. What I'm doing is basically 1 is that index 1, right? Index 2, index 1 and 2, right? Like this. So, and there could be 1, 0 when you take 2 and 3, 0 when you take 3, and it could be 0, 1, 0 when you take 1, 2, 3. It could also be 0, 0 when you take 1, 3, right? Let's see, are all permutations covered? All right, so right, out of these possible subsequences, right, out of these possible subsequences, which are the beautiful subsequences? Because it's given that we have to choose the beautiful subsequences. So this is beautiful. This is also meets the condition. This meets the condition. This meets this one also, this one also. But this doesn't, because 0, 0 cannot be adjacent, right? So therefore, the number of possible beautiful subsequences would be 6 for the input n equals to 3. Right? Similarly, you can find it for other also, like n equals to 4, n equals to 6. For n equals to 6, somebody asked the doubt, and I did reply it there also on the Discord group. And the number of possible subsequences were 32. Right? You can just go through each subsequence and check if it's a beautiful or not. And this way you can find 32 possible subsequences. Right. So the question is pretty simple to understand. You'll give an n, right? And you have to find the number of possible subsequences. Okay. Right. Now let's try look at the approach for this. So let's first look at the brute force approach. Right. What could be the brute force approach? Well, it's kind of obvious that you generate all possible subsequences of the given input. So you give 1, 0, 1, 0. So just like I did here, I found out the all possible number of subsequences for the given for the sequence, and then I just check if it's beautiful or not. So right, you can generate all possible subsequences and check if for each you can check the condition if it's beautiful or not. right? So in that way, you can do it. But and how do you find all the subsequences? We just use a recursive algorithm, right? That just adds 0 or 1 to the end, and it just checks, right? It's a recursive algorithm, and it checks each step you check it. So it's recursive, so it would be something like 2 power n. And given the input range, n can be 10 power 6 also. So this kind of algorithm wouldn't work because, you know, this exceeds 10 power 8, right? 1 second. 10 power 8 iterations is 1 second. So that is why it exceeds that. And that is why you need to come up with a better optimized approach, right? So as you know, this is something related to DP. So let's think of breaking down the problem into sub problems, right? How can we break down it to sub problems? Right. Let's look at it. So let's see if you've given this subsequence, given this sequence of length, from 0 to I minus 1, let's say, right? And this is the I. So, right. Now you have been given this. So if you know that for this sequence, right, what are the possible number of sequences, right? So let's assume for this, for I minus 1, the number of possible subsequences for I minus 1, right? Our algorithm has given us this x I minus 1, which represents the possible beautiful subsequences till I minus 1, right? Now you come across a new ith element, right? This new ith element could be right. 1 second. Now, first let's clear one thing, that these possible beautiful subsequences include the I minus 1th element, right? These include I minus 1 element, which could be 0 or 1, right? So now what would be the ith element? Now we come across the new element, ith element. If I minus 1 the element is 0, then ith element would be 1 because it's given the input is beautiful subsequence, right? And if it's 1, it would be 0, right? Right. And now, if it's not clear right now, what we can do now, what we have to find is possible beautiful subsequences till I, right? This includes the ith element, right? Now, if you have all the subsequences like this that end with 0, right? You have subsequences, right? All subsequences. And what you want to do is just append the ith element to that particular subsequence, right? So if this was the earlier subsequence and it ended with 0, right? On a subsequence that ended with 0, I'm assuming I minus 1 is 0 right now. On a subsequence that ended with 0. And this was the I minus 1 the element. And these were all the subsequences for that, right? Now, when ith element comes, what you want to do is just, when you want to calculate for ith element, you just want to append the ith element here, right? And this is for 0, 2. So these were x I minus 1, right? So when you append this the ith element to all these, what you get is xi minus 1, right? Xi minus 1 possible subsequences. Plus, there would also be one more subsequence. What would be that? That would be the single ith element, right? That is 1, right? So basically here, this possible, only this would also be considered as a possible beautiful subsequence, right? So that is why we add x1 to it. Okay. So if xi minus was the possible beautiful subsequences till I minus 1, so possible subsequences till I would be xi minus 1 plus 1. Right? Yep. And here we solved for if I minus 1 element was 0. The same could be done for if it was ending with 1, this I minus 1. If these subsequences were ending with 1, right? And you just append the ith element. Ith element would obviously 0, right? Here you can see. And for this here. And you can see you can just append 0 to it. And similarly, you will get xi minus 1. And then you just add 1 to it. Because, this 0 would itself be a possible beautiful subsequence. Right? Easy. Now, if this approach is clear, let's try look into its implementation. How would we want to implement it? So before we are doing these operations, what we are doing is right. So, yep. Now our ith element, it could be 0, it could be 1, right? If it's 0, we would want to append it to subsequences ending with 1, right? And for if its ith element is 1, we want to append to subsequences ending with 0, right? So it's obvious that we want to maintain both these quantities as we traverse our subsequence. As we traverse our sequence, right? So we want to maintain it. So let's just keep an array A for it, right? That maintains these two quantities. This represents that it ends with 0. This represents it ends with 1. Okay. And initially, when we are starting our algorithm, these both values would be equal to 0. Okay. Now, of course, we want to maintain something like our DP array, right? And even if we don't maintain it, it's no problem. Let's just maintain, okay, we maintain this array, it's sufficient for that. Okay. Now, okay, so now let's formalize this approach. Now, when we come to the ith element, ith position of the sequence, what we are going to do is what would be xi minus 1? Xi minus 1 would be one of these quantities, right? Either it could be A0 or A1, right? Now, if xi minus 1 was odd, right? Then we need to, if it was odd, another condition if it was even, right? If it was odd, This means this quantity, right? So xi would be, as we know, xi minus 1 plus 1, right? Which would be a1 plus 1, right? Because if I minus 1 was odd, if I minus 1 position was odd, then we need to consider this value, which will give us the odd values that were at that position, right? Okay, let's look it with another approach that would be more clear. Right. Now let's consider if ith position was odd, and under condition if it was even. So what would be xi? Xi is xi minus 1 plus 1, right? And now if I is odd, right? I is odd. This means that we need to consider all those subsequences that were earlier ending with 1, right? And we need to append 0 to it. Sorry, that were ending with 0, right? All those sequences that were ending with 0, right? And then we need to append 1 to it. That is odd, because 1 is odd, right? This means this represents it was 0, I equals to 0, and here it represents I equals to 1, right? I'm so sorry. It represents I equals to 1, and this represents I equals to 0, right? So we want to append 1 to it. So we consider all those subsequences that were ending with 0. So here is our value, right? A 0, right? We maintain this value, we'll do a 0 plus 1. If ith position it was 0, I'm going to do xi minus 1 plus 1 and append 1 plus 1, right? Okay. And once we have done this, we also need to update a1 now, right? Because we have increased the number of subsequences ending with 1. So we need to update it. How do we update it? Earlier a1 plus xi, right? And here we update a0, right? That is a0 plus xi, right? And one operation would be common to them. What would be? In our final answer, we'll just add xi for both the operations, right? Because we are maintaining all those possible subsequences for all i's, right? So at each I, we have to update our answer. So this is how we update the answer, right? I hope it's pretty clear right now. Let's write let's write a pseudo code. All right, so we have our A array. We will initialize our A array 0, 0, and our final answer to 0, right? And now what we're going to do, we're going to loop through all the positions from I equals to 0 to n minus 1, assuming indexing is starting from 0 right now, okay? And what we're going to do is find xi, which would be A. Now, how do we get now, right? If I was odd, how do we check if I was odd? Do an AND operation with 1. When you do AND operation with 1, it could give 0, it could give 1, right? If it gives 0, this means I was even. And if it's give 1, it means I was odd, right? Because if here you calculate 0 and 1, right? It gives us 0. This means it was even. 1 and 1 gives us 1. This means it was odd, right? So that is why you could do I and 1. And now we have to choose opposite of it, right? Here you check that when it was odd, we took this one, right? So that is why you do AND operation of it. So when I is even, right? If when I is even, it returns 0 and gives us this position, right? This is what we need. No, this is not what we need. When I and 1, when I is even, I and 1 gives us 0. But here we saw when it was even, we had to take A1, right? So we have to take this one. So that is why when we do AND of it, AND of 0 gives us 1. It gives us this position, right? Hence, we have got the correct position, right? But if I was odd, I and the AND operation gives us 1, right? It gives us 1. And when I was odd, we have to consider A0, right? So not of 1 will give us 0. So that is why we get this position, right? So our algorithm above matches this, right? So that is why we have taken AND operation over here. And we do +1, right? And now we update. Once we have done this, we have to update A1 for odd operation, right? So here we don't take any AND, right? Not, sorry, we take AND and we don't take any NOT. And we just update. Right. And we update our final answer also by X. And then finally just return an answer. So this is what our pseudocode would look like, right? I hope it's pretty clear at this point. If any doubt, please let me know in the chat box. Right. Now, let's look at the code for this solution right now. And our algorithm is pretty clear, right? This is what we are doing. Okay. Code part. Let's come to the code part. So now let's look over here. What we are doing is taking the input n, right? And then we have defined another function beautiful for the main algorithm part, right? So our function will call this our code will call the beautiful function, right? With input n, right? Now there is the algorithm where it starts. We have initialized this vector, right? And we have initialized our answer. Initialize our final answer. And actually, this wasn't necessary. What I'll do is just remove it for now, right? Okay, so what we do is here, make x equals to a, and what position we enter is and of I and not of I and 1, right? And we add 1 to it. And then we are taking mod also, because in the question, if you see, it is specified that you have to take, modulus at each operation, because there could be large number of possible subsequences. So that's why taking mod over here, right? And that is how we calculate x, right? You can see that x is being calculated like this. And now we update our position, right? A, I and 1. We add x over here, right? And we do a modulus, like we take mod of it. And we update our answer also by x, right? And this is what we get. Sorry, in text. right? So what 3, n equals to 3, we are getting 6, right? Let's enter 6 over here, n equals to 6, we should get 32, right? We're getting 32. Is correct. Let's, you know what, let's dry run this and let's see what is actually happening for these inputs. Okay. Now, let's take our input n equals to 3. That is, we are given 0, 1, 0. Right. Let's initialize our A 0 and 0. Right. And we initialize our answer equals to 0. Now, let's start. I equals to 0. Right. We are looking at this position. So for I equals to 0, we should get 1, right? Because 0 is only possible, right? So for I equals to 0, what happens? When you take I and 1, 0 and 1 gives us 0, right? Not of 0 is equal to 1. So x equals to a1 plus 1. What is a1? This is 0, this is 1, right? a1 is 0, so 0 plus 1 equals to 1, right? X equals to 1. And then I and 1, right? Here, I and 1. A0 equals to A0 plus X. A0 here, right? We've updated to 0 plus 1 equals to 1. So here we updated to 1, right? Yes, we updated to 1. And we update our answer. Answer becomes answer plus X, that is 0 plus 1 equals to 1. So here we update our answer to 1. Okay. This is happening for I equals to 0. Now when we go to I equals to 1, what happens? I and 1, 1 and 1 gives us 1. Not of 1 is 0. Now x of a0 plus 1, right? So now a0 plus 1, what is a0 plus 1? A0 is 1. So what we do is 1 plus 1 equals to 2. And now we update a1 equals to a1 plus x, that is a1 was 0, right? So 0 plus 2 equals to 2. So we update this a1 to 2, right? And our update answer plus x, that is 1 plus 2 equals to 3. So this updates to 3. Now let's pause here for a minute. Let's now not go to I equals to 2. Let's first look what has happened over here. If you see, for I equals to 0, the sequence was just this 0, right? When I equals to 1, right? So at position 1, 1 comes here, right? 1 comes here. Then, as you remember, what we're doing, appending this particular to all those subsequences before, right? So 0 was a subsequence before. So we'll append 1 to it, right? And 1 would also be a single subsequence, right? So that is why we get 2 over here, right? And here you see, we have updated it to 2, right? And earlier this was 1. So 1 plus 2, it becomes 3, right? Remember, this is x, right? xi, that is x1, right? That is what we were doing over here above, right? So this means our algorithm is working right till now. And let's finally take for I equals to 2. What happens is I and 1, 2 and 1, it gives a 0 because 2 was even. So now x becomes, so not of 0 is 1. So a1 plus 1, right? What was a1? A1 is 2. So this is 3, right? We update a0 now equals to a0 plus x. That is 1. A0 was 1. So 3 plus 1 is 4. So we update this to 4. And we update our answer to answer plus x. X was 3. So answer was 3 plus 3 equals to 6. So we update our answer 3 to 6. And if you see, this is our algorithm's ends over here. And what we get is answer equals to 6, right? Finally, we have got this, which is the correct output. You can dry run this code for other possible, inputs also, like 6 or maybe 4, and check if it's working right. It will work right. Okay. I have showed you the dry run for n equals to 3, right? So just do it similarly for other. I hope the code is also clear what we are doing over here. I'll comment it. We're doing xi equals to, right. I've already showed it, right? So, yep, this was the explanation for week 10 programming assignment question 2.
Yeah, so like I will explain the week 11 question 1 problem statement. Let me share my screen. So this is the problem statement. I hope it is clearly visible now. So some sort of story has been formed in order to confuse you guys. And in most of the CP problems, you find such type of stories. The important thing is not to get distracted by the story and to read those slowly, understand the problem statement, and boil down these long and lengthy questions to algorithm like basic math understanding. Okay, so let's read the story. In a small town, there was a treasure hunter named Lily who had heard rumors of a secret treasure hidden deep in the forest. She set out on a journey to find the treasure, and after days of wandering through the forest, she stumbled upon an n cross n array. Okay, n cross n array. So we have an n cross n array of integers that held the key to her treasure. Okay, the array represented a treacherous path to the treasure, with each integer representing the number of traps that lay in that location. So if the integer here is x, then this represents the number of traps that are in this particular location. To reach the treasure, Lily had to follow falling path that started at any element in the first row, and choose the element in the next row. Go from this row to this, from this to this, and up till the last row. Choose the element in the next row that was either directly below or diagonally left or right. So this means that, let's say if you are on this particular element, then you can go here, or you can go here. Okay. So this is diagonally left, this is down, and this is diagonally right. Okay. Lily knew that she had to be careful and find the safest path that would minimize, important word, her risk of getting caught in the traps. She wondered what was the minimum sum of any falling path through the array. So the question is, forget about all the story about Lily, about traps, about treasure, and the question just boiled down to n cross n array being given. Okay, and you start from this row. You want to reach the end row by, let's say, like every entry in the array is an integer. Okay, is an integer. So you have to find a path from the first row first to the last row, which is also called the falling path, such that the sum of integers encountered in the path is minimum. Okay, so yeah, that is the whole question. Let's understand the input. The first line of the input T input contains T the number of test cases. So we have T the number of test cases. The first line of each test case contains the integer n, representing the number of rows and columns of the array. So for each test case, you will have n, which represents the number of rows and columns, and then we will have a n cross n array. Okay. Looking at the constraints, again, as I had said before, constraints are very important because you always want to propose an algorithm which should obviously not exceed the time limit. And again, I will tell you guys the time limit is 1 second, which is 10 power 8 operations. To try to propose an algorithm which the algorithm should operate in less than 10 power 8 operations. Okay, so try to find out such an algorithm, and output is just to print a single integer indicating the minimum sum of any falling path through the array. Okay, so the question is quite simple. You are given a n cross n array. You start from the first row from any element and you reach to the last row to any element, and the condition is that if you're standing at a particular element, you can go directly below, or you can travel diagonally left, or you can travel diagonally right. Only these three cases are possible. So again, all possible cases, you need to explore all possible cases. And as I had said before, whenever you encounter these three words, all possible cases, you directly think of a DP solution. Okay, so this is a hint. So yeah, let's see the test cases. The first test case is this. So this is the array 7748. So this is a 2 cross 2 array. 2 cross 2 array. If I start from here, let's say if I start from here and go here, this will be 7 plus 4, which will be 11. Another possible is from 7 to 8. This is 7 plus 8 is equal to 15. Or possibilities from 7 to 4. This is again 11. And from this 7 to this 8, this is again 15. So the minimum of all these is 11. So 11 should be our answer. Yes, it is our answer. Okay. Looking at the next test case, which is a little bit bigger, 6426. So the array is 6426, 11 6, 11 9, 6 3 4 10, 4 3 9 2. Okay. So in this particular 4 cross 4 array, what could be the minimum falling path sum? So I can look at an path which starts from 4, goes to 6, then to 4, and then to 2. The sum would be 4 plus 6 plus 4 plus 2, which is equal to 14. And out of all the possible cases, this is the minimum. And you can try to explore all the possible paths, and you will find that 14 is the minimum answer. 14, or what is the answer? 14. Okay, so this is 16. Okay, so this is 16. Okay, so forget about this 4. I picked this 2. So from this 2, go to 6, go to 4, go to 2. So this will become 2 plus 6 plus 4 plus 2, which is 14. So out of all the paths, 14 is the minimum answer. You can try exploring all the possible cases. So I think the question statement is fairly clear and it is very easy to understand. You have n cross n array. You just have to find the minimum path falling sum by exploring all the possible cases. And as I had said before, whenever you think about all the possible cases, think about recursion, and recursion will eventually lead you to a DP solution, which you will have to think. So just a hint that you will have to use a 2D DP in this case, unlike week 10 programming question 1, which I had explained, which was a 1D DP problem. This is a 2D DP problem. Think about something of DP of IJ. What will DP of IJ represent? Okay, this is one hint which I'm giving to you guys. All the best. So that's all from my side for week 11 programming question explanation. Thank you.
Yes, Satvik, do you want to explain week 12?
Okay, sir. Yeah. So in this problem, what we're given is an array A of distinct integers. Of distinct integers of length n. You want to construct a beautiful array. A beautiful array. Using the elements from the array A, and we have given the definition of what is a beautiful array, that is for any pair of numbers A and B, which satisfies the following condition: A percentage B and B percentage A is equal to 0. That is that either B is divisible by A or A is divisible by B, right? And then you have to output the largest possible beautiful array using the given array, right? Also sort the resultant array. So from the given array, you will have to pick certain amount of elements, right? You're given an array A and you'll just pick a certain amount of elements from it, such that if you pick any pair of numbers, which we denote by A and B, either A should be divisible by B or B should be divisible by A, right? So let's look at the example from which we'll know better. So here we are given this array 1, 16, 7, 8, and 4, right? Now this is our array A. You have to pick some elements from it such that, right, such that this condition is met. What elements could you pick? If I pick 1, 4, if I make array like 1, 4, and 8, right? You see that in this array, if you pick 1 and 4, 4 is divisible by 1. So this checks out, right? If we pick 4 and 8, any two pair of numbers, right? 4 and 8, then 8 is divisible by 4. So this checks out. If you pick 1 and 8, it also checks out, right? Another array, possible array could be just 4 and 8 also, right? In it, 4, just like 4, 8, 16, right? If you pick 4 and 16, 16 is divisible by 4. So that's what this is, right? And if you pick 8, 16, you can take 4, 16, right? But if 7, if you pick something like 1, 7, and 4, right? If you pick 1 and 7, this checks, right? If you pick 1 and 4, this also right, because 4 is divisible by 1. But if you pick 7 and 4, not 4 is divisible by 7, neither 7 is divisible by 4, right? So this is not right. So this means this is not a valid beautiful array. Okay. Now, if you check, this is a beautiful array, this is also a beautiful array, but none of them is the largest possible array. The largest possible array would be 1, 4, 8, and 16. Right? This is the largest possible array. You pick this one, you don't pick this, you pick this, right? Okay. So this is how it happens. If 1, 2, 5 is given as the array, you can you pick 1, 2, 5? No, because 2, 5. Oh, shit. 2, 5 is not valid, right? So you can only pick 1, 2 as a pair, and which is given in the answer, right? Now this is what you have to do, right? You have to output the largest possible beautiful array using the given array, and the constraints are given to you. The number of test cases can range from 1 to 10. The length of the array can be from 1 to 10 power 3, and each element can range from 0 to 10 power 8. The time limit is 1 second. That's 10 power 8 iterations. So, just think in what direction you can solve this question so that you can, definitely this is possible by brute approach, but just try it on your own. See if brute force approach works over here or not. Yeah, this is the problem. Thank you.
Yeah, okay. Thanks, Atvik. Thanks, Sahil.
Yeah, thank you, sir.
Thank you, sir.
Yeah, you can leave.